Okay, wow, it looks like it's here. You got my invitation. That's good. So going forward, as far as I know, now, even though this class has been scheduled to run for the rest of the semester, I think that you do need a new link every week or every class. So I'll be sending them out by email, just like I did over the weekend. And my goal is to get it to you within a day or so before the class meets. If I forget, which occasionally happens, I'll just make sure it gets to you before we start. So if you don't see an invitation in your inbox, let's say the day before, it probably will arrive by that morning. But if not, you can always send me an email and just say, hey, what's going on here? And chances are what's going on here is that I forgot. So let me show you the email. Now, by the way, I do want to point out too that the email that I used to send you your invitation is not my purchase email address. It's actually this address, which is my email address. And the reason for that is because your roster, I have your roster in an Excel spreadsheet. And in order to send out an invitation, my goal is to send it to the entire list all at once. Now, for whatever reason, the SUNY purchase email system doesn't allow me to take an Excel spreadsheet and convert it into a list. So instead, I'm using my own Gmail account. Okay, so that means there's actually two email addresses you can use to get in touch with me. One of them is my official email address at SUNY Purchase. This is the one that I use for my own emails, but you can write to either one of these. In fact, let me show you the other one on the syllabus, which is on Moodle as we speak. In fact, let's go visit Moodle for a second and see what's going on there. Let's see, I got so much stuff open. I'm gonna have to go find it. Hold on, here we go. Here's Moodle, and your page is right here. And so you notice that there are a few things already on here. There's a syllabus, and there are chapter 5 notes, which I've broken up into 3 parts. And there's also a video link, which we'll be using today. And so if we open up the syllabus, let's see, where is it? Here we go. Here's the syllabus. Now, you'll notice here that the email address on the syllabus is my purchase account. You can use either one of these, but later on, we'll discuss this later on, when you are submitting assignments, I'll ask you to use the purchase account just because it's easier for me to find them. But for most other communications, I often end up using my personal account just because I look at it all the time. And, you know, let's face it, it's also got the superior ability to send out the notifications. So I'll be using both of these as we go throughout the semester. All right, anyway, so here we are again. And you can see it's pretty unpleasant outside. And so today's one of those days where it pays to be online, isn't it? Now, as far as I know, all of the classes are online this week anyway, but starting next week, only the actual online classes are online. Everybody else is expected to come back and do in-person classes. So for our purposes, the entire class will be online. Okay, we'll be meeting every Monday and Thursday at 10:30 until early May sometime. And of course, my office is not available to me. My office will be where I live, and that will be a virtual office. And my office hours, TBA, means that if you need to go over some materials or have any questions, you can either send me an email, or else you can arrange to have a private Zoom session just between us. So that's why TBA, which of course stands for to be announced. My phone number's in here. You should probably save that for actual emergencies. You know, that, like, if I'm in the hospital, I can't come to class. That's when you use the phone. Okay, for anything short of that, emails are quite sufficient. Anyway, so then here's my purchase email address, and it does work. It just doesn't work very well with sending out notifications. There is a book for this class, but you probably don't have access to the bookstore anyway. But if you do, it's in there. All of these sections of this class use the same book, and it's called Math in Our World, Media Update. And you can see it hasn't been updated in quite a while. And so for that reason, I'm not sure if there's a PDF version of it online, or if there's some kind of an electronic version of it, it may only be available as a physical book. Now, having said that, you don't actually have to have that book for this class, because all the notes are actually written already in my PowerPoint slides. If you want to use this as a reference, or if you just want to read more about the material that we're covering, then you can go ahead and buy the book, but it isn't required for this class. Okay, this is the book we're leaning on. This is what we're using, but it's not mandatory for you to go out and buy it unless you really want it. Anyway, now, here's a very important topic that we need to discuss right up front. And by the way, this gives me an opportunity to show you a very cool feature of these Zoom meetings. It actually has the capability of conducting polls. And so what I would like to do, just for the fun of it, is ask you with one of these polls, what is your situation with your calculator? So hold on a minute. No, it's being very stubborn with me today. She's all right. I'll start a new one. Here we go. This will be our first poll of the semester. Here we go. Do you have a physical calculator? Okay. So it's pretty easy to set this thing up. This will be a simple yes or no question. And now I can actually use it. Here it is. So I'm going to launch the poll. Now, what I'd like you to do, of course, is answer yes or no. This is more out of curiosity than anything else. Okay, well, that's a pretty big percentage of yeses, I mean. I always ask this question at the beginning of the semester. So now I have to use the poll system. All right, now, if you do not have a physical calculator, that's fine. And I'll tell you why. Oh, by the way, I just realized my camera's not even on. Here's why it doesn't really matter. Because I know that pretty much all of you, if not every single one of you, has this little device. And if you look on it, you may not have ever noticed this before. Oops. Let me see if I can. I'm not used to this camera thing. Right about there. What do you see? It's backwards, but it's a little app, and it's called Calculator. Now, this comes on your phone when you buy it. You don't have to download it. It's already there. So I'm going to turn mine on and show you that it has a very basic calculator, which is fine, but it's not going to be enough for this class. So how do you get around that little problem? Watch this. If you turn it sideways, it converts itself into a very powerful scientific calculator, which is perfectly sufficient for this class. All right, now, if you've never seen this before, we're going to get a lot of practice with it during the course. And so it's important to learn how to use it properly, because every calculator is a little bit different. So we'll use it as we go along. So if you don't have a calculator, you can use your iPhone instead. If you do have a calculator, you can either use the iPhone or the calculator. It's up to you. The goal here is to get you comfortable with one calculator that you can always use, not just in this class, but for any other classes that you might take that involve math. So if that's the case, if you've got one that you're comfortable with, that's fantastic. Even then, though, there's probably some new features that you're not aware of. Now, some of you may have one of the really high-powered ones. The classic example of that would be the Texas Instruments series. For example, the Texas Instruments, let me make that a little bigger here. Texas Instruments TI 83 or 84, or something in that neighborhood. These are extremely powerful. If you already have one, that's fantastic. A lot of what we're doing in here, you can get a lot of use out of your calculator. If you don't, I wouldn't go out and buy one just for this class, but if you have one, you might want to, take the full advantage of it. And so as we go along, I'll be explaining how to use all these different calculators. All right, but you do need a calculator. All right, that's the bottom line. So if you don't have one, like I said, that's fine. I'll teach you how to use the iPhone. And by the time we're done, you'll see that it is a very powerful calculator. All right, what else do we need to know about this class? Okay. Oh, okay. Now, the material that we're covering. Now, it looks like that's not a lot of chapters, but each one is fairly long. So all of the information you need, like I said, is in these slides, which I've written for you to cover all the material that we'll be doing. And then as we go along, we'll also be covering a lot of practice problems. So there's none of them posted here just yet, but soon enough, we'll start working on these practice problems together to make sure we really understand the material. And then somewhere along the way, we'll have exams. Can't be helped. We have to have exams. This is, after all, a math class. So it turns out there's going to be 3 of them, 2 midterms and a final. And of course, we will review before each one of these. And don't even worry about it. It's going to be a long time before we're ready for midterm number 1, probably not before the beginning of March. Okay, it's going to be a while. But before we get to that point, we'll cover all the material, and we'll also do all the practice problems, and then we'll also review for the exams so that everything that's on these exams will be known to you in advance, and you'll have no problem with them. That's my opinion. You'll have all the information you need. There will be no surprises. It'll just be exactly what we've been doing during the class. All right. So what else do we need to know? I think that pretty much covers it. If I've forgotten something, I'll let you know later on. But yeah, okay, so that's good. So that's our syllabus. Now, let's see if there's anything on Moodle we also need to know about. No, we just have our syllabus, and what you should ideally be doing is reading through the slides before each class starts, just to get some comfort level with the material before we get into it. That way it'll make more sense to you while we're actually in the classroom, or the online classroom, I should say. Occasionally I'll post links to videos which we'll be watching during the class. These are all there to give us some background information about what we're doing here. And I think you'll find these videos to be extremely helpful because they will give you a sense of how this math was developed and what is it used for. Okay, and in fact, a lot of these topics that we're covering can be used for a lot of very interesting and exciting applications in the real world. And that, I hope, will help give you more understanding of the material that we're covering. So I've got a lot of them ready to roll. And so we're going to watch them throughout the semester. And I'm hoping that gives you a more complete experience, shall we say, as far as the math is concerned. All right, now, I'm going to do another poll right now. I usually do this at the beginning of each semester anyway. It's just that I'm usually there in person. So I'm going to ask you this question. And just out of, again, this is just out of curiosity. Let me start it up right now. Hold on. Yeah, here we go. How long has it been since your last math class? Okay, so the choices will be less than 1 year, 1 to 2 years, and finally more than 2 years. And again, this is just out of curiosity. I'd like to find out how long you've been away from math. So let's get this one going. All right. This is pretty much what I was expecting. It's been quite a while for several of you, but I think you'll find that as we go through this material, a lot of it you may have already seen before, but it's possible that you've started to forget what you learned. And that's okay, because as we go through it again, it'll all come back, and this will hopefully add more to your existing background so that you'll have more knowledge of math, and also maybe you'll enjoy it a little bit more. That would be kind of nice. All right, now there's one more question I want to ask. Then we can get started. Math, let's say, how much do you like math? All right, this is just, again, this is just for the fun of it more than anything else. I love it. I'm okay with it. And don't ask. All right, those will be your options. All right, let's see how that turns out. All right. So these are pretty. I mean, I'm not surprised to see these numbers. This is pretty much what I would have expected. This is what I've seen in the past. There's a few people who love it, which means you may actually go on and take more classes, which is great. In fact, you know, the school offers a full semester of statistics, which I just finished teaching during the winter break, and that would be the next logical step after this class, or possibly pre-calculus, which I also teach. For the rest of you who maybe have decided this is it, no more math for me, that's fine. Hopefully, though, that the don't ask people move into the at least the okay category by the end of the course. All right, the more you find out about math, the more you learn about it. I think the more background you have, I think the more you'll appreciate it, and that's part of our goal here. It's not even just learning the material, that's fine, but it's important that you understand what it's for and get some sense of where it's coming from. So those are some of our many goals for this course. In the early course chapters, like I said before, I think you'll recognize that you probably remember a lot of this material. It's just that it's been a while since you saw it before. So eventually we'll get into the more complex material, and we'll take it from there. But I'm going to essentially assume that you don't remember any of it and essentially start from scratch with all these many different topics. All right. Now, oh, but you know, I just realized too, one more question I can ask you. Let's try this one. Welcome back. Is this your first class of the semester? Yes or no? All right. I'm going to have to guess that the answer is yes, but let's just see. Wow, we've got some no's in there. So some of you had a class at 8:30 then. Wow. Okay. So then it's not a complete shock. You're back. Well, you're not completely used to it. It does take a little getting used to, especially after such a long, extensive Christmas break. But okay, so you know, obviously part of the challenge today is to get back into the swing of things and get used to being in school again. And so hopefully on a crappy day like this, it won't be that painful, because what else would you be doing anyway? So, all right. So why don't we get into the material? We're going to start looking at chapter 5, as I said. This is the first portion of it, chapter 5A. And the title of the chapter is The Real Number System. Now, it turns out that all numbers, I'll add a new slide here for this, all numbers fall into one of two categories. One of them, of course, is real, but the other one is something you might have not been exposed to before. So I don't need to do a poll for this. You can actually answer questions in this chat box. If you want to type it in, who knows, or does anybody know what the other type of number is? Okay, imaginary, yes, that is exactly right. So now what we have to do is remind ourselves what it means for number to be imaginary. Yes. So already we're brushing all the cobwebs off of our math knowledge, and we're thinking, man, it's been a while since I thought about imaginary numbers. So let me remind you what that is all about. If you were to take the square root of 1, a negative 1, now you know that in principle you're not supposed to do this. But it turns out that there are branches of math where you are actually allowed to do this. We're not going to do that here, but this I represents the square root of negative 1. This is an imaginary number. Now, we're going to see in one of our videos this semester, there's a brief discussion about what this actually means. And so we'll save it until that video. But what I do want to point out here is that in this class, we will not be dealing with imaginary numbers, okay? Only real numbers in this class, all right? So now you're all breathing a sigh of relief. I can hear it through the computer. No imaginary numbers. That's great. So we're going to look at only the real numbers. You're welcome. Okay. If you want imaginary numbers, you have to go into pre-calc, or at least, but not here. This is just all real numbers because this is meant to be a very applied class. And I just want to remind you, and you've seen this before, how are they illustrated often in math? We usually represent the real numbers with something called the real number line. So we can put any numbers we want on here. And with the understanding, these arrows mean that they go all the way up to positive infinity and all the way down to negative infinity. And all the real numbers are here. Now, what I have not labeled are the fractional ones, like, for example, 0.70214 or 1.5067 or maybe negative 1.212. So all the real numbers are represented on this diagram. And so you can see the number of real numbers. It sounds odd, but the number of real numbers is infinite. Okay, so bear that in mind. There are an infinite number of real numbers on that number line. And what we're going to do is we're going to start out by classifying them into different categories. And these categories actually reflect the development of mathematical thinking over the centuries, as you'll see when we watch our video later on. We're going to start out with a very simple case, which is the so-called natural numbers. Now, if you look at this carefully, you'll see that this notation is meant to indicate that this is a set. And if you recall, a set is a collection of objects. That's all that it is. And in this particular case, you'll notice that we have these dots here to indicate that this pattern continues forever, all the way up to positive infinity. So therefore, there are an infinite number of natural numbers. And of course, if you look carefully, you'll notice that these are the numbers that we use to count things. So these are often referred to as the counting numbers. And as you'll see in the video, early humans used these numbers to keep track of, for example, what season it was, or how many chickens they owned, or anything that involved numbers. They were going to use natural numbers because none of the other numbers really were needed, and they were not thought of yet. So these are the natural numbers. These came first. And so it is an infinite set. And you'll notice we don't have 0 in here. There's no negatives and there's no fractional values. Okay. Now, we're going to now remind you of this very important concept, which I'm sure you've seen before, of factors. It turns out that all natural numbers can be expressed as the product of a set of factors. Now, what do I mean by that? Let's think about 12. What pairs of numbers give me the value of 12? Now, by the way, here we're only restricting ourselves to the natural numbers. You notice how there's no negatives and there's no fractions. I just want the natural numbers here. So I can write 12 as 1 times 12, or 2 times 6, or 3 times 4. So we say that 1, 2, 3, 4, 6, and 12 are the factors of 12. Okay, the factors of 12. Now, if you look carefully at these numbers, you'll notice they all have one important thing in common. What could that be? If I take 12 and divide by any of these factors, let's say 4 or 6 or 3, in each case, I have what's called a quotient, but what I don't have is a remainder. Let me show you, and like if I tried 5, for example, I would have 2 and 2/5. This is my remainder. When I divide a number by its own factor, there is no remainder. Or you can think of it as having a remainder of 0. It means the same thing. So what these all have in common is that if I divide them all into 12, I'll get some quotient or other, but no remainder. Well, you've heard it. The term that we use to describe this is that we say that 12 is divisible by its factors. Or sometimes you may have heard it expressed this way, 12 is evenly divisible. Sometimes you hear it written that way or described that way. Is evenly divisible by its factors. That's how we know that they're factors, because they evenly divide into 12 with no remainder. And that's what they all have in common. All right. So now, with all that being said, all right. Well, of course, we know that those are all the factors of 12. Now, what we're going to do next, in fact, this is my challenge to you. I hope you have paper with you, because we'll be doing this throughout the course. Of course, this isn't being graded or it doesn't count or anything, but what I would like you to do is take out a piece of paper and write down the factors of 24. All right. Now, I don't want to rush you, so I'll give you a couple of minutes. Just sit down and write out the factors of 24. So hopefully you've got pen and paper there somewhere. If not, in the future, you should probably try to make sure you have some just in case. All right. So I'll give you a couple of minutes and you let me know what you come up with. All right. Was that enough time? So you can use the chat room. Wow. Here it is. So enter. Oh, that's a lot of numbers. I'll tell you what. Let me just show them to you. So what you're basically trying to do is identify all the pairs of natural numbers whose product is 24. And this is the complete list. And that tells me that 1, 2, 3, 4, 6, 8, 12, and 24 are the factors of 24. All right. Now, the biggest challenge with factors is actually missing some of them. It's easy to overlook some of them. So, you want to be careful. But one thing I do want to point out here is that I did not list separately 6 times 4 because that obviously means the same thing as 4 times 6. So this is the complete list. Those are the factors of 24. Now, this is interesting for, by itself, but it turns out we can actually use these factors for important applications. So what we're going to do next is revisit, well, first of all, the concept of being divisible. I think we understand that now, but let's just quickly remind ourselves. In general, if we have two natural numbers, A and B, if A over B has a remainder of 0 or no remainder at all, that means that A is divisible or evenly divisible by B. And that's all that it means. Okay. So for example, let's say 25 is divisible by 5. Since 25 over 5 gives us a quotient of 5, there's no remainder. Okay, but 25 is not divisible by 4 because 25 over 4 would be 6 1/4, and this is our remainder. And you can see it's not 0, so therefore 25 is not divisible by 4. Okay, 5, yes, but not 4. All right, now with that being said, we're going to bring up a topic, a special type of number that you know about, but you probably haven't thought about in a long time. Okay, so, but here in this slide, we're just reminding you that each natural number, I should say, is divisible by its own factors, but there's a special type of natural number that we want to think about, and that is the so-called prime number. Oh God, who remembers that? Prime numbers. A prime number is a number that only has two factors, 1 and itself. So therefore, a number like 7 is prime because the only two factors that it has are 1 and 7. 7 is not divisible by any other natural numbers besides 1 and 7, and therefore it is prime. Yes, prime numbers. When was the last time you thought about prime numbers? It's probably been a while. You don't run into them. Well, you do run into them in practice, but you don't necessarily just think about it like that. So why don't we look at a list that I put together of the first 10 prime numbers. But before we do that, I just remembered there's a very strange exception that we have to consider. It turns out that if you want to be really technical, 1 is not considered to be a prime number. Why not? because to be prime, we need two factors. Actually, what I should say is two unique factors. One and the number itself. You don't have that with one, do you? There's only one factor. Or I guess, again, I should say one unique factor. And that's one. Therefore, it does not qualify as a prime number. That seems a little strange, but it's true. One is not considered to be prime. It's it's an exception. You might think, wow, isn't it? It can only be divided by one in itself. But since there's only one factor, it is not formally defined as a prime number. So what about the actual prime numbers? What are the first 10 prime numbers? All right, let's take a look at the list. Here we go. Now, again, you'll notice they will have something in common. There is no natural number that evenly divides into any of these. Okay. So obviously, except for the 2 itself, this rules out even numbers, doesn't it? A number like 10 or 4, they can be divided by 2. Therefore, they can't be prime. But here, the only way we can divide these numbers is by 1 and the number itself. And of course, you can go on and on and on and on. The number of prime numbers is infinite, as you can imagine. And it turns out that finding prime numbers is actually quite a bit of a challenge. Mathematicians have been trying to find a program that generates all the prime numbers, and they've not succeeded so far. Apparently, it's much more challenging than it looks. But now it turns out, though, that there's a very interesting application of prime numbers that you might already be very familiar with. So I'm going to do a little poll here. And when I do it, you'll say, wow, what an interesting poll that was. Do you shop on Amazon.com? Yes or no? Wow, it seems like a silly question, doesn't it? Oh, I forgot. The question goes here. All right, that's okay. Not a problem. So let's run this through. I'm pretty sure I know what the answer is going to be. Oh, we got to know. 2 no's. Wow. I'm kind of surprised in this day and age. Is it because you don't like Amazon, or is it because you don't like to shop online? Well, whatever the reason is. Now, the reason why I brought this up is when you shop in Amazon, what actually happens? You put all the stuff you want in your cart, and then when you order it, you give them your name and address and all the rest, and then you give them a credit card number. Now, that information gets transmitted to Amazon's computers, and then they, obviously process your order. Now, here's the big question. What's to stop crooks from reading your credit card number by hacking into your computer or Amazon's computers? Well, here's how this works. Let me just throw this in here. What's happening here, and you may have heard about this. Okay, what's going on here? PowerPoint is being stubborn with me. This is really weird. What's going on here? All of a sudden, PowerPoint is not cooperating with me. I don't have a good relationship with technology. Let's put it that way. Yeah, something's wrong here. I'm going to turn this off and turn it back on again. Yeah, technology often gives me trouble. You'll discover that throughout the semester. It knows when you don't trust it, I think, is what happens. So just like that, PowerPoint decided to stop working for no reason. Anyway, so when customers order merchandise from Amazon, their information is transmitted wirelessly to Amazon's computers. Okay, so in order to prevent the information from being stolen, the numbers are encrypted um, using a code that is only known to Amazon. So, in other words, when it goes through the internet, well, when it goes through wherever it goes, I don't understand it myself. But what's happening is that, yes, the information is out there where somebody could theoretically see it, but it's all been turned into a code of some kind that nobody but Amazon knows how to interpret. And then when it gets to their computers, they reinterpret it as the original information. Okay, so the reason why I'm mentioning this example is because the codes used are often based on prime numbers. So in other words, the methods that they use to encrypt your information is often based on a program of some kind, which is itself based on prime numbers. Now, the reason why I know this is because I actually know somebody who is a specialist in this area, and it is a very, very intense area of study because, you know, it's very hard to stay ahead of crooks. No matter what's going on, no matter what century it is, it's hard for law enforcement to stay ahead of crooks. And so here, the technology makes it possible for the good guys to stay one step ahead of the bad guys, but it requires a lot of sophisticated mathematics. And that at some point does come down to prime numbers. There's something about prime numbers that lend themselves well to these encryption schemes. So that is the only example I can think of off the top of my head of how and when prime numbers can come in handy. Okay. So the next time you're ordering something online, just be aware that there's a lot of security going on behind the scenes to keep the bad guys from stealing your information. Same thing with banks, like all that online banking that you do, it has to be heavily, heavily protected because there's so many crooks out there who would try to steal your numbers and then steal all your money. Okay, so anyway, this all falls into an area called cybersecurity, which is obviously a hot new area for people who are good at math and who are interested in law enforcement. Anyway, so it turns out that all the natural numbers that are not prime numbers have another name. They're called composite numbers. Okay, so in other words, all the natural numbers have to be either prime or what we will call composite. And composite simply means that the number has to have a minimum of 3 factors. It has to have one, the number itself, and then at least one more to be considered composite. So here, for example, you can see that 22 must be a composite number because in addition to 1 and 22, it also has the factors 2 and 11. And that's enough to conclude that 22 is a composite number. Okay, so all of those natural numbers are either prime numbers or else they are composite numbers. All right, now we're going to tie all this together into a very interesting way. It turns out that while each of these numbers that we've been considering has typically multiple factors, except for one, in fact, they all have at least 2 factors. It's convenient sometimes to decompose those factors into prime numbers. And we're going to do that right now with a special technique, which is called prime factorization. And all it means is that we're going to take each of our natural numbers and break them down into a series of prime factors. Okay, so this will make more sense when we actually do it. Prime factors. In other words, factors that are all themselves prime numbers. And it'll turn out that each of these numbers, each composite number, I should say, can be uniquely expressed as a product of these prime factors. And once we learn how to do this, we'll see at least one application of these prime factors. Okay. All right, now let's go back to the example of 12. We know that 12 has these factors. Now, by the way, I've left out 1 and 12. We're only interested in these numbers right now. We don't want the 1 because it is not prime. So we have these 4 factors, 2, 3, 4, and 6. Now, what I would like to do, though, is rather than write it out this way, I would like to use a special type of diagram, which I think you'll find very helpful. And in order to carry out this process, what I'm going to do was first, let's just point out that if I take either of these sets of factors, 6, for example, can be rewritten as 2 times 3. So 12 equals 2 times 6, but 6 itself can be written as 2 times 3, which means that I can write 12 as 2 times 2 times 3. And so because these are all prime numbers, this is what we're going to call the prime factorization of 12. Now, I can do this in another way. Remember, 12 also equals 3 times 4. 4 equals 2 times 2. So I can combine those to the following statement. 12 equals 3 times 2 times 2, which is the same thing as 2 times 2 times 3. So this is what we call the prime factorization of 12. And again, it is nothing but the product of prime numbers, and that is unique to 12. Okay. All the other natural numbers will have a different prime factorization. All right, now I'd like to show you that graph that I mentioned, how to take a number like 12 and break it up into its prime factors. We're going to create something which is called a binary tree. Can be used to identify a number's prime factors. Now, of course, you know that bi means 2. So that means we're creating a tree which always has 2 branches coming out of each number. And those branches lead us to factors of 12. So what we are trying to do is continue the tree until we've identified all of the prime factors. So like here, for example, I can stop with the 2 because it's prime. Over here, when I have 6, I don't want to stay there because I need to break it down into its prime factors, which are 2 and 3. So this chart or graph is showing me something interesting. Whoops, hold on. It's showing me the fact that my prime factorization is 2 times 2 times 3. Now, that wasn't that hard, was it? Let's do another one just to make sure we get the hang of it. Let me just randomly pick, I don't know. How about 40? We could break it down into 2 times 20. Now, 20 is not prime, so I'm going to rewrite that as 2 times 10. 10 is not prime. I want to write that as 2 times 5. And now I'm done because these are all prime numbers. So I can say that the prime factorization of 40 is 2 times 2 times 2 times 5. This is what we mean by the prime factorization. Okay. Do we all see how that works? So you're breaking it up. Good. Beautiful. Oh, I didn't see that remark before. Who does have a good relationship with technology? There are people who get along well with technology. I'm just not one of them. I don't understand it. I mean, I want to love it, but it doesn't want to be loved. That's the way I look at it. It always lets me down whenever I really need it. And that's not good. So, all right, anyway, I'll tell you what. Now, here's my challenge. I want you to try this with, let's say, 90. I'm just randomly picking 90. So I would like you to create a binary tree for 90 and use it to identify the prime factorization of 90. All right, I'll give you a minute to take care of that.
All right, I think I did it.
All right. So how did you do it?
So the tree from 90 is 3 times 30.
Okay.
And then 30, not a prime number, so it'll be 2 times 15.
Okay.
And then, oh, I didn't do 15. It's okay. It will be 3 times 5.
So usually we put them in order. It's 2 times 3 times 3 times 5. Now, what's interesting here is that you can do this usually in different ways. Like, what if you'd started like this? I could have done 2 and 45, 5 and 9. But you see, it turns out the same. It's still the same numbers. And that means 2 times 3 times 3 times 5. So when we say that the prime factorization is unique, that's really what it means. It means no matter how you go through this tree, you're always going to wind up with the same prime factors. All right. So, and of course, everybody likes to draw, don't they? I think pictures are easier to follow, I think, than just words. I think there's something about the way our brains are structured that pictures are what makes the most sense. The language, actually, the written language came much, much later in our history. Pictures were always the way to go. It's just writing came in much, much later because you notice that a picture really sticks in your mind. You can remember it so much more clearly. Yes, they are, absolutely. So that's why whenever possible, I like to use diagrams to illustrate what we're doing rather than, writing out sentences, which certainly makes sense, but we all know that pictures are the way to go. Okay. That's just who we are. All right. Now, it turns out that there's something useful we can do with these prime factors. And this requires us to recall a concept which we've all been exposed to. And when you see this, you're going to say, oh, it's been so long since I thought about this. It's almost like an old friend coming to visit you that you haven't seen in like 5 years. All right. So here we go. Be prepared for a bit of nostalgia here. We're going to reintroduce the concept of Here we go. Greatest common factors. Sometimes they're called greatest common denominators. What does that even mean? It is the largest number for two numbers. Let's say this is the greatest common factor for two different numbers. It is the greatest integer that evenly divides both numbers. So here's an example. 18 and 24. What is the largest number that evenly divides both of these? Well, if we wrote down a bunch of numbers, eventually we would figure out that it's 6, okay? But it turns out there's a quick and easy way of doing this that takes advantage of our newfound knowledge of prime factorization. So I'm going to show it to you with the graphs. I mean, the slides have a discussion about it too, but I'd rather show you the graphs right now. We're going to do the following. We're going to do a binary tree for both 18 and 24. Yes, so there should be room to do both of them on this slide. And again, the sequencing that you use is not important. What matters is that you get the final result correct. So for 18, we have 2 times 3 times 3. For 24, we have 2 and 12, 2 and 6, 2 and 3. Um, 24 equals 2 times 2 times 2 times 3. Now, what are we looking for here? The greatest common factor equals the numbers, the factors, I should say, that they have in common. So in other words, they both have a 2 and they both have a 3. So therefore, the greatest common factor is the product of those two numbers, which is 6. Oh, well, that's pretty clever. So these prime factors have at least one very useful feature. I can use them very quickly and easily to identify greatest common factors. That's right. Now, you probably ran into a few of these on the SAT test that you took to get into the school. I don't know. I don't remember any longer if that was on there or not. It's been so long since I took it, but it sounds like something that you would have seen there. But if you did, it would have been nice to have this technique in front of you because look how easy it is. Oh, they're crazy. Oh, it's worse than that. Oh, okay. Yeah, I'm not surprised. They probably tightened it up since I was that age. Wow. So, yeah, you don't actually have to take the SAT for some. I think some of the departments don't require it anymore, but it's a good way to sort of separate yourself from other applicants to the school. So even though sometimes it's not mandatory, I think still it's a good idea to take it. At the very least, you'll review a lot of the information you learned while you were in high school and keep it fresh in your memory. Anyway, did you all have to take, oh, that's a good poll. Were you required? Because the trend is getting away from those standardized tests, I believe, in education. Let's create a new poll. Were you required to take the SAT for your major? This is just out of curiosity. I'm just wondering if this is, I mean, when I was at that age, everybody had to take it, no matter who they were. All right, let's check this out. This is just more out of curiosity than anything else. Uh-oh, there we go. Yeah, look at that. It's majority of the people said no. Interesting. Like I said, I'm sure it depends on what major. Like if you're applying to the math department, I'm sure they would have expected you to take. But if you're studying dance, let's say, or any other performing arts, it's probably not very meaningful. They more likely they would have had like an audition, let's say, or something like that. Is that about the size of it? Is anyone here in one of those performing arts programs? Did you have to
I
audition?
am
Oh, okay, what are you studying?
vocal performance opera.
Okay. Oh, opera. It's funny. I tend to get a lot of opera majors in this class, for some reason, or at least more than you would expect. And so, how do they decide if you get in or not? Did you just sing a song for them or something?
So it's a pre-screen audition. So you
Uh-huh.
have to send in 3 videos of you singing in Italian, German, and French.
Oh,
And then if they like you, they invite you to come audition for them in person.
I see. Okay. Yes, I want a math opera too. One of you has to write that math opera. I know it can be done. It's possible. But you know what? There actually have been a few plays about math on Broadway, but not an opera that I know about. Um, there are a few. I'll mention them as we go through the course, that you might find interesting. Um,
Definitely.
well, you know what? Now, like for example, the one I can think of off the top of my head. This was on Broadway, but it's also a movie with Anthony Hopkins. If you just sit down one day and say, "I want to watch a math movie," yeah, I mean, it's not really like it's all math. It's about a mathematician, is what I should say. It's called Proof, and it was on Broadway. It was a movie and very interesting because it's about basically a crazy mathematician,
Oh, okay.
and it's well done. I mean, you know Anthony Hopkins. He's been in like Silence of the Lambs. He's been in everything.
Yeah,
Something you
he's
want to.
incredible.
You don't have to know anything about math to appreciate it. You just have to know that mathematicians do proofs. That's as far as your knowledge needs to go. Oh, you did read that. Oh, how did you like it?
It was good. I was forced to read it for class,
Oh,
so I had no choice. But it was
well,
good.
it was worth what reading it, wasn't it?
Yeah.
It was kind of sad though. I mean, he was losing his mind. I mean, come on. But all right. Anyway, so yes, that's out there, and there's others too. And if I can think of any more, I'll mention them. But occasionally, math slips into the popular culture. It happens. It's been known to happen. Um, so all right. Anyway, so oh yes, so I got a few other interesting responses. Some people are in acting, and some people are in creative writing, film. So again, with acting, how do they decide? Do they ask you for a video? Um, I'm not sure how that would work. So that's probably, yeah, I can see that. Design technology. Yeah, these would definitely be all areas where you probably don't need the SAT because, oh, in-person audition. Okay, well, that would make sense. Wow. I'm not sure if I could deal with that. Oh, A Brilliant Mind. Yes, yes, yes. That's another good one. That's about the economist John Nash. Same kind of idea. He was losing his mind, but he did eventually win the Nobel Prize in economics. Um, yes, Beautiful Mind. That's right. That was well done as well. Okay. It was sad, but it had a happy ending. So now, interestingly enough, as far as that goes, the author of that book was Sylvia Nasser, who's a writer for the New York Times, and I actually know her husband because he was one of my professors at Fordham, and he'd said that the Nashes had been to their house a few times, and apparently John was fairly well recovered, but he was still a little bit nuts at the end. But that's all I know about it. All right. Well, anyway, let's get back to this now. What we're going to do here is as a challenge, since now you see how this works. What I would like you to do is calculate the greatest common factor of 72 and 180. All right, I'll give you a couple of minutes. So you'll need two trees. And then, of course, you'll gather up all the factors and find the ones that they have in common and then multiply them out. All right, whoever has their number can let me know to the chat room. Okay, now 9 is a common factor, but it's not the greatest. I don't think 15. Yes, it's 36. Okay, very good. We have a winner. Kelsey Collins is the winner of this contest. All right, so let me show you why. So we'll do the two trees side by side. So let's try 72. So I'll do 2 and 36, 2 and 18, 2 and 9, and then 3 and 3. Okay, so it has a lot of factors. No, don't be like that. You're going to be very good by the time the course is over. So it's just, we're going to, after 2 more of these problems, you'll be as good as anyone at this. Okay, so 72 equals 2 times 2 times 2 times 3 times 3. And for 180, 290. I usually do 2 whenever it just seems more systematic that way. And of course, you can't always do that. Like this is 3 and 15. Okay, same. Yeah, no. You'll be very good by the time we're done. Okay, 180. It's like that show. Have you ever seen that show, The Worst Cooks in America? Well, you can probably figure out what it's like. All right, what happens? They get together people who can hardly boil water into the kitchen, and then they teach them skills. And by the time they're done 8 weeks later, they're cooking for a professional audience, and they're actually getting pretty good at it. Okay, so they go from not even being able to use a can opener to being able to make nice dishes, and it only takes them about 8 weeks. So we've got 16. So that means it's understood that by the time 16 weeks are up, you're going to be awfully good at this. And I mean good, not just okay, but good. All right. So that's what we're looking at here. We're looking at future mathematicians who don't realize it yet. All right. So anyway, so this one is 2 times 2 times 3 times 3 times 5. Okay, so now here we have to be careful. Just pick out what they have in common. They both have 2 2s, and they actually both have 2 3s, don't they? So therefore, the greatest common factor is 2 times 2 times 3 times 3. Guess what? That is 36. And you can tell if you try to divide them both into, let's say 72 divided by 36 is 2 with no remainder. And 180 divided by 36 is 5 with no remainder. So there is no larger value for which this is true. Okay? Yes. Okay. Oh, all right. Go ahead.
So, all right. So math isn't my strongest.
Okay. Well, guess what? It's nobody's strongest point in this room.
Right. Well, I'm glad. Yeah, I'm glad I'm not the only one. So I just want to clarify so I can sort of figure it out myself. So what we're doing here is dividing until we can no longer divide. So like we would stop at 3 because you can't take anything.
That's right. You can't go any further. That's
Okay.
right. Yeah,
Cool.
that's all it is. You stop as soon as you can't go any further.
Gotcha.
And then
And
you
that's
gather them all up.
and that is finding, or is that's I don't want is that finding the greatest common?
Well, this is part of the process. Here, what you're doing is you're looking for the prime factorization. Okay. Once you have that for both of them, then you look for whatever's in common. Those numbers are multiplied out to give you the greatest common factor. Okay, so we're going to do one more just to get you some more practice. And you'll see the third time around, well, second actually, you're going to say, oh, come on, it's too easy. Now, this time it's a real challenge. Yes, that's what you're going to say. There's 3 numbers involved. Is that possible? Yes, it is. You just need 3 trees. All right. So believe me, after a few of these, you're good. Okay. Even the worst folks can learn how to use the can opener. Eventually they get it right. It's the same thing here. All right. All right. Give this a shot. I'll give you a few minutes. And then when this is done, we're going to watch our cool history of math video because I think you'll enjoy it. And it gives you a good background and perspective about what we're doing here. Oh my God, did somebody already get it? Ooh, I'll tell you what, I'll save that. I won't say yes or no until everyone's done. All right. Okay, now we've got several guesses. All right, let's wait another couple of minutes. By the way, I do want to give everyone a hint. You might find a number which is a common factor, but maybe not the greatest common factor. Just a little hint. All right. I see a lot of eager beavers who want to know if they're right. We'll just give people another minute or so. You know what, I'll tell you what, let me start slowly. I'll just draw the trees. Start with 24. We got plenty. See, did you upgrade your? Yes, you did catch on to what happened. Okay, good. All right, let's try this. So 24 breaks down to 2 times 12. 12 is 2 times 6, and 6 is 2 times 3. So these are my prime factors. Now we need 72. Now we already did 72 before, but this is still very good practice. All right. All right, so for 72, we have 2 times 2 times 2 times 3 times 3. Okay, and then we still need 120. I'll do that on the next page. Let's try 260, 230, 215. Okay. 2 times 2 times 2 times 3 times 5. All right. Now, in order to make this work, I'm going to put them all up here in the same place. Okay, 72. So you can easily see what they have in common. And then 120 is 2 times 2 times 2 times 3 times 5. Well, they all have 3 2s and a 3 in common, which is 24. You got it? Everyone got it? Yes. You see, now all of a sudden it's easy. What's going on here? Why were people thinking it was hard? It's not hard. Okay. So yeah, it just takes a couple of tries. You know, once you've done a few of these, they're all very similar to each other. Well, I'll try to avoid having any numbers that are so large that they have like tons of these factors. But yeah, in a nutshell, this is how it works. So we had a lot of good, if I go back to the chat room, I see a lot of people got it right. Now, if somebody got 12, that just means you missed one of them. You missed one of the 2s, that's all. It is, in fact, 24. All right, so now your reward for all this hard work is that you get to see a fun video. Now, here's one thing we have to be careful about. Let's go back to Moodle. The link is on your Moodle page. Let's go get it. Now, here's what I have to watch out for. Oh, wait, now I lost my place. Oh, here we go. So because we're recording this class, the videos are copyrighted. And so what I've been informed is that I should not record the video. So we're going to watch it, but I'm going to pause the sharing. So that way, if you watch this video later on, the video that we're watching now will not be part of it. But you can still watch it with this link. So right there, you'll see the history of math. It's about 6 or 7 minutes long, and I think you'll find it to be extremely interesting. And it's about how number systems evolved over time and what people use for numbers. So what I'd like to do is for everyone to click on this link and then watch the video. I'll watch it right here too, but it's not being recorded. And then when we get back together, we can talk about how much fun it was. Okay. All right, here we go. Let's click that thing on and let's carry it on, carry on.
We can't see the video.
Oh, did you click on the link on Moodle? Oh yeah, it's over here. In fact, you know what I could do? Let me just in case it's a problem, I can send you the link by the chat room. Yeah, no, I want everyone to watch it on their own screen because you won't be able to hear the sound anyway. That I do know. For whatever reason, the sound will not come through the computer from if I'm watching a video. So I need everybody to watch it on their own screens. Are we all pretty much done with that? Pretty interesting, huh? That's right. You can see math really does have a very interesting history, and we're not done with it yet. We're going to see a lot more of that. In fact, I believe on Thursday, we're going to see a video about the history of zero. And you might say, well, how cool could that possibly be? But I think you'll be surprised by how cool zero really is. And so, you know, you don't think about these things. You just take it for granted that zero exists, but somebody had to think of it. And so it took a long time before zero made its introduction into math. And the history of zero is actually quite exciting. And then there'll be others. For example, we'll be looking at a video that really explains why we can't divide by zero. Now everybody knows you're not supposed to do it, but they're going to tell you exactly why, the exact reasons. And I think you'll find that quite interesting. But sadly enough, I think that for today, maybe even though it's a little early, it is the first day, which means maybe we don't have to spend the whole time here in class. I think we've gotten a lot covered, and why don't we knock it off right here, and we'll just meet up again on Thursday. And if you want to watch the video, it might not be ready for a little while. It takes time for it to be converted into MP4 format, but by tonight, it'll be available on the in our playlist for this class, which, by the way, I don't think I mentioned that earlier. The Zoom itself works well for a lot of things, but it's not good for storing videos. So I was told that the best bet for storing all of our videos would be to put it on YouTube. So in order to find our videos, you need to go to YouTube under my account, of course. And when you get there, there's playlists, which I've set up so that, because otherwise there's going to be a bunch of them all jumbled together. You'll want to look for the playlist for our class, Matt 1060, 1030 p.m. a.m. And it's not there now because there aren't any videos yet. But when I start populating it, you can just go into the playlist and you'll see that it's in there. And then you can find any of our videos and watch them whenever you want to. Okay, so they'll always be there waiting for you if you want them, but you're not required, of course, since you were already here. But you never know, you might have missed something, or maybe you want a further explanation. So anyway, so the videos would be here. And then other than that, I think unless somebody has last minute questions, I think we're done for today. And so you may want to think about staying inside, and unless you're a skier or something. And then we'll pick it up on Thursday. In the meantime, what you should probably do is flip through the slides and remind yourself, you know, what we've been doing. And what you might want to do, because we're almost done with section 5A, is actually take a look at 5B and see what we're going to be doing on Thursday. Okay. Other than that, I think we're done. So, all right. I'll see you all next time. All right. Bye.
Bye. Thank
Take
you.
care.
Thank you.
Okay.
Bye.
Bye.
Is it okay if I ask a question real quick?
Yes, it sure is.
Okay, so just to clarify, we don't have any impending assignments.
No, not yet. No, in fact, what we're typically going to be doing is we will, when we get through with a certain amount of material, we'll have a bunch of problem sets that we'll work on together. And then really the only things that you'll be ultimately handing in are the 3 exams. The rest of it will just practice with. Yeah. So there's no I mean, I could give you a bunch of busy work to do, but I think it's easier if we just practice the problems together in class. And then,
Oh, yes.
then that means all the weight is on the exams. So you just have to be careful that you do well on the exams.
Right. Okay.
Technically, the only assignment you have is to just keep up with reading the notes and make sure you understand them. That's it
Okay.
for now.
Okay, well, thank you very much.
All right, you're welcome.
Take
All
care.
right, see you Thursday. All right. Okay, bye.